Hello and welcome to our lesson on more identities. What we're going to do in this particular topic is just build off of what we've been working on for the previous two topics. We're talking about trig identities, which are just statements of inequality. And remember, the purpose of these identities is to do a few different things. One of them would be simplifying trig expressions. One is to evaluate trig expressions, or also to solve trig equations. Now I know we haven't done any of the solving yet, but that's because we haven't talked about all of the identities yet. So we're going to add to our list of identities, add to our list of equality statements to help us in these processes of evaluating, of simplifying, of solving, or even verifying. I think I didn't mention that one the first time. Now I will tell you that in my 18 years of teaching, I have not used all of the identities that are on this paper here, or all of the identities that I have talked about. And I am not going to attempt to string you through an example where each of these is used, nor am I going to attempt to show you the proofs for any of these, because ultimately the goal is the same. We just got to be able to identify when one of them applies to a certain situation and try to apply it. And if we can apply a few of them, the chances are we can apply the rest of them. Okay, so we're going to go through a few examples again just to try to build off of what we've been working on for a few topics, and hopefully by the end of this you'll feel okay working with what we call the double angle, power reducing, half angle, or product to sum, sum to product identities. Okay, so those along with the unit circle are going to be helpful here. So let's look at our first example. The first one says, well, we're going to use double angle identities. It says, given that the cosine of x is equal to negative 2 over radical 5, and that sine of x is positive, to determine the cosine of twice our angle, and the sine of twice our angle, and the tangent of twice our angle. So again, double angle identities here. Now, we got to start with our given. So first, cosine is equal to negative cosine of x is equal to negative 2 over radical 5, and the sine of x is positive is important information. So if we're talking about our unit circle, okay, where in quadrant 2, if cosine is negative and sine is positive, we have to be in quadrant 2. So I would start this particular problem by drawing out a right triangle in quadrant 2. So I'm going to draw out a right triangle in quadrant 2, as tiny as I can make it over here. I'm just not sure how much space I'm going to need, so I'm going to try to work small and make my triangle in quadrant 2. Okay, so let's say that this is my angle x according to this. If the cosine is negative 2 over radical 5, then we would have negative 2 for an adjacent side and radical 5 for our hypotenuse. And I put the negative with the 2 since that's on the negative part of the x-axis. Okay? Because we have the Pythagorean Theorem, we could figure out our missing side. So we could say that a squared plus negative 2 squared has to equal radical 5 squared. So that's a squared plus 4 equal to 5. If I subtract that over, a squared has to be 1, which means a has to be 1. So now, not only do I know that the cosine of x is equal to negative 2/5, I can also say that the sine of x is equal to the opposite side over the hypotenuse, so that's going to be 1 over radical 5, and I can say that the tangent of x is going to be the opposite over the adjacent, so that's going to be a negative 1/2. So now I know the cosine, sine, and tangent of x, which will help me in finding the sine, cosine, and tangent of 2x. Okay, so one at a time here. I'm going to start with the cosine for 2x. Okay, just using the rule that's at the top of our paper here, in that first box of our double angle identities, we actually have 3 options for the cosine of a double angle. It can be cosine squared u minus sine squared u, twice cosine squared u minus 1, or 1 minus 2 sine squared u, and all of those are going to be possible here. I'm just going to choose to work with this first one, although it doesn't matter, all 3 of them would actually work. So I'm going to go with the cosine of twice an angle is equal to the cosine squared of the angle, not twice the angle, but the angle, minus sine squared of that angle. Okay, so this is actually something I have enough information to evaluate. I know the cosine of my angle. It was given to me. It's negative 2/5. So this is going to be negative 2/5, negative 2 over radical 5 squared. Right, there's my cosine x. I just have to square that. And then sine, we figured out from our right triangle, was 1 over radical 5, and I'm going to square that as well. So I have values for sine of x and cosine of x. I square those. That's going to give me the value for cosine of 2x. So negative 2 over radical 5 squared is going to become a positive 4 over 5. And then minus 1 over radical 5 squared is going to be 1/5. And 4/5 minus 1/5 makes the value of the cosine of 2x 3/5. Alright, so we got one part of that done. Let's try another part. Change colors. So next, let's try to evaluate the sine of 2x. So again, just going back to our sine of double angle here, it's twice the sine of u times the cosine of u. Twice the sine of u times the cosine of u. So in this case, it's going to be twice the sine of x times the cosine of x. And again, those are things that I know. So this is twice the sine of x, we said, was 1 over radical 5, and the cosine of x we were given was negative 2 over radical 5. So when I multiply here, I end up, this is a 2 over 1, so I end up with 4 on the top of the fraction. It's going to be positive, positive, negative, so negative 4 on the top of the fraction, and then a radical 5, and radical 5 makes 5 on the bottom. So negative 4/5 is the value for the sine of 2x. And then lastly, let's look at the tangent of 2x. And again, just going off of the table, tangent is twice. The tangent of 2x is twice the tangent of x divided by 1 minus tangent squared x. And again, tangent of x is something that we determined. Over here we said tangent of x is going to be a negative 1/2. So we're looking at 2 times the tangent of x, which was a negative 1/2. And that is divided by 1 minus the tangent of x squared. So a negative 1/2 squared. And that becomes, the 2 times the negative 1/2 on the top of the fraction is negative 1. And on the bottom, the negative 1/2 squared, this part here, becomes a positive 1/4. And then 1 minus the 1/4 is going to be 3/4. So the bottom of the fraction becomes 3/4. And a negative 1 divided by 3/4 is the same thing as a negative 1 times 4/3, which makes our final result negative 4/3. So we did it, okay, using a little bit of right triangle and Pythagorean Theorem stuff and our double angle identities. We were able to figure out the values for the cosine of 2x, sine of 2x, and tangent of 2x. Exact values, okay? Hopefully not too bad. Moving right along, and so that I don't have to keep scrolling all over the screen, I went ahead and snipped some images in of the identities we're going to be using. Next, we're going to look at the power reducing identity. So power reducing, and notice in the identity, the power of sine goes from 2, and we end up with a cosine with the power of 1, and a cosine power of 2 down to a cosine power of 1. So power reducing is just that. It's trying to go from a higher degree to a smaller degree. In this case, trying to express the sine to the 5th power of x. So sine 5th, it's hard to even read that. Sine of the 5th power of x in terms that contain only first powers of sine and cosine. So this is a 5th power of sine that we have to reduce down. The first thing I would do is think about just normal exponent rules, right? If I had something like an x to the 5th, I could say that that's x squared times x to the 1st. I could separate that out because ultimately these all get added to make the 5 that we have here. That's the first approach I would take. That way I can apply my sine squared and or cosine squared properties. So I would say first that the 5th power of sine here is going to be the same as sine squared, and sine. Okay, so there's all 5 of them just separated out, but now that we've separated them out, I can replace each of those sine squareds with what that's equal to using our identity. So the first sine squared becomes 1 minus cosine of 2x over 2. And then the second one becomes the same thing, 1 minus cosine 2x over 2. And then I have this last little sine of x hanging out here. And right now, we haven't really changed or haven't really reduced our powers because we're trying to write this in terms, and each of the terms can only, or in terms that contain only first powers of sine and cosine. Now right now, because this is still one giant product, it's still one giant term. If we were to multiply it out, we still have a higher power of cosine here, which means we're not quite done. So we need to try to simplify. And the only thing I can think to do to simplify here would be to go ahead and multiply out these two binomials. So if I do that, the 1 times the 1 is going to give me 1. And then I'm going to have a negative cosine of 2x and another negative cosine of 2x, which is going to give me negative 2 of the cosine 2x's. And then, oops, so come on, pen. And then when I multiply here and here, I'm going to get the cosine squared of 2x. And that's going to be negative, negative, so positive. So this would be plus cosine squared of 2x. So there's foiling out, I'm distributing out the top of the fraction. On the bottom, the 2 times the 2 is a little easier. That's just going to be a 4. And then that still needs to be multiplied by the sine of x. Now the fraction makes this a little bit complicated, and I don't want it to be there, so I'm actually going to factor that 1/4 out. If I just multiply by a 4th here, and then 1 minus 2 cosine 2x plus cosine squared 2x, and then sine of x for me just looks a little cleaner. I don't know that that's completely necessary, but we still have a higher power in here, which is no good. So I'm going to, let's see here, I'm going to replace that one now. We know that the, goodness, pen. We know that cosine squared is 1 plus cosine 2x over 2. So I'm going to apply that identity now in this spot. Get rid of that higher power of cosine. So let me keep going here. Oops, I'm going to turn my pen back on. I'm looking at now this 1/4, which was an optional thing to do. And not actually a good option, because when I go to replace cosine here, it's going to make another fraction, and a fraction within a fraction is kind of a mess. So it's good of me to take that 1/4 out. Now I'm going to have 1 minus 2 cosine 2x, and then cosine squared over here of x would be 1 plus cosine of 2x. Now in this case, our x is already 2x, so this would be 4x, and then divided by 2, and then we still have this sine out here. Okay. Now, I know that this is still one giant product, but if we were to multiply out this product, the only thing we would have to multiply in would be the 4th, which is not going to change any powers there, and then the sine. And if I was to distribute in a sine here or here, I would still have sine to the first power, and I would still have cosine to the first power, which means we have gone quite far enough. Okay, we've gotten everything in terms of a sine or cosine with a power of 1, and so we can consider this an answer. It's ugly, definitely doesn't look any more simplified compared to what we started with, but we're able to reduce the powers. And I don't know that we're going to solve any equations that are this complicated, but this is a process that's helpful when we go to solve. Just think about solving polynomial equations, right? When we're solving a 5th degree polynomial, that can be kind of complicated. Whereas if we could reduce the degree down to something linear or quadratic, we have a lot more tools for solving for those lower power, the smaller power or smaller degree functions. The same is going to be true with our trig function. So while that does not look any cleaner than it did in the beginning, having the smaller powers is going to help us when we get to solving in the future. Okay? All right, moving right along. We're going to look next at the half angle identities. So the sine of half of an angle, the cosine half of an angle, and tangent of half of an angle. And here we're trying to find the exact values for sine, cosine, and tangent of pi-eighths radians, which is half of what? Now maybe your brain thinks well in fractions. If you can see it, awesome. I'm not so good with doing that, so I would probably convert these radians to degrees. If I was to convert pi over 8 radians to degrees, I would have to multiply by 180 over pi, and those would cancel, and 8's actually not going to go into 180. This is going to reduce to 2 and 45, so we're going to end up with 45 over 2, 22.5 degrees, but I wouldn't even make that a decimal because what we want here is something that's in the form of being divided by 2. So this is perfect. 45 over 2 is perfect. It's like I set this up or something for the notes. So I'm really looking to evaluate the sine of 45 over 2 degrees and the cosine of 45 over 2 degrees and the tangent of 45 over 2 degrees. Okay, so now we can apply each of these. Let's look at it. So let's start with, I'm going to call this 1. On the first one, we know that the sine of x over 2, in this case 45 is going to be our x, right? The sine of 45 over 2, it's going to equal plus or minus the square root of 1 minus the cosine of x. So x, remember that's the top of our fraction there, is just 45, so it's going to be cosine of 45. Get rid of that. And then we're dividing by 2. So cosine of 45, that's just from our unit circle. A 45-degree angle hits the unit circle at radical 2 over 2 and radical 2 over 2. So the cosine is radical 2 over 2. And so this is going to be 1 minus radical 2 over 2 over 2. And we generally don't want to leave fractions within fractions there. So I would probably simplify here by just multiplying by a common denominator of 2 every single one of those terms. So we're going to have plus or minus the square root of 2 times 1 is going to be 2. And when I multiply the 2, again, 2 times 1 makes 2. When I multiply it here, the 2's will cancel, leaving me a minus radical 2. And then when I multiply the bottom, I'm going to end up with a 4. So we're here. I could probably factor out a fourth from that, and I might want to do that because I can take the square root of a fourth, but if you got this far with it, I'm really okay with this as an answer. Let me show you what I'm saying. If I just look at the radicand, if I factored out a 1/4, then I would still have a 2 minus radical 2 here, and then I would just have a 1 on the bottom, so 2 minus radical 2. And I might want to do that because I can square root this part of it. So then I would have plus or minus 1/2 on the outside of the square root of 2 minus rad 2. Now to me, this does not look much better than this, so I don't see the point in really taking it that far. But you know, if you see those things and you want to keep going, you totally could. I'm going to stop it there and say this is the exact value for the sine of 45 over 2, which was pi over 8. And this is something we could verify with our calculator. So let's go ahead and do that. Let's make sure we're in radians, and we are. So let's put in the sine of pi over 8, gives us a decimal. And now let's put in our our result. I'm thinking about, I don't know, my brain. So let's put a fraction under here. This is 2 minus radical 2, and then on the bottom a 4, and there is our same exact decimal. Okay? So there's the first one. Let's look at the next. The next one being, let's call this number 2. Okay, cosine. Now if we look here at the the variation between sine of I'm on my pen. Between the sine and cosine of x divided by 2. The formulas are almost identical. The only difference is we have a negative here and we have a positive here, so I would not go through all this work again. I know just from the work I did in the first one that the second one here, my cosine of 45 over 2, I should be putting the degrees symbol in here, is going to be equal to almost the same thing. We're going to end up with 2 and then a plus radical 2 divided by 4. And again, that's something that we could confirm with the calculator. And so now I'm just going to work on this last one. So the last one, number 3 here, says to figure out, let's go with the tangent of 45 over 2 degrees. And a couple of options. I'm going to go with the first one. The first one says to take 1 minus the cosine of x, and remember x is 45 here, so we want the cosine of 45, and then it says to divide that by the sine of x, so the sine of 45. And again, at 45 degrees, our sine and cosine are both radical 2 over 2, so this becomes 1 minus radical 2 over 2 over radical 2 over 2. And again, I would clear out these fractions. Let's multiply by 2 here, and here, and here. And so we end up with 2 minus radical 2 over radical 2. And I'm okay with it in that form if you wanted to rationalize the denominator. 2 radical 2 minus 2 might be a prettier answer, but I am totally okay with this as an answer as well. And let's go ahead and confirm with the calculators. We had already kind of confirmed the other two, so let's do this one. Let's make this the tangent. And it's going to give us that decimal. And let's put in 2 minus rad 2 divided by rad 2 and make sure we get the same decimal. Always nice when it works out. Sometimes you lose a little bit of, I don't know, maybe this is just me. I lose a little bit of my confidence sometimes. Gets to be late at night, make goofy mistakes, but always nice to know when we did these things right. Calculators are our friends. Okay, I got one last one I want to show you here. And so we found some exact values. We did a little bit of, I don't know, rewriting here. Last one, we're going to do a verifying problem. It says use the sum to product identity. So turning a sum into a product, just like it says, okay, to try to verify that this expression is the same thing as the tangent of 3x, which seems crazy that that would simplify down. So remember, when we're verifying, we can pick one side and try to simplify down using our identities to make the one side look like the other. So on the top of the fraction, we have the sum of two signs. So we're going to rewrite it using that first identity there, where in this case x is 2x and y is 4x. So it says here to start with 2 times the sine of x plus y. Well, if I add our x and y, the 2x and the 4x, I get 6x, and it says to divide that by 2. And then we're going to multiply by the cosine of x minus y. So x minus y is 2x minus 4x, which would be a negative 2x, and that gets divided by 2. Okay? On the bottom of the fraction. On the bottom of the fraction. This time, x and y, again, 2x and 4x, but it's the sum of cosines, so we're going to apply this second one here. So we're looking at twice the cosine of x plus y, so again, 6x over 2, and then the cosine again of x minus y over 2 again, so again, a negative 2x over 2. Now this is all one term on the top, this is all one term on the bottom, and the fact that we have a product on the top and a product on the bottom means if we have anything in common to the top and the bottom, then we can reduce. So for example, we have factors of 2 that we can reduce, and we have factors of cosine of negative 2x over 2, and I know that simplifies, but those reduce. We don't need those, okay? So what's left for us is the sine of 6 divided by 2 is 3, so it's the sine of 3x divided by the cosine of 3x. And we were trying to show that this is equal to the tangent of 3x. Well, tangent is defined as sine over cosine. So if we have sine over cosine, it is precisely tangent of 3x. And there it is. We did it. Okay, we were able to show using our identities that that mess that we started with on the left is exactly tangent of 3x. Okay, so it's really helpful for you to be given directions, right, to tell you what to use. But just look at your problem and see if something in one of those boxes can be applied to rewrite if you aren't given the direction. Although I think in the problems I will give you, I will try to lead you a little bit. All right, so I know this can be a little challenging. It just takes practice like everything else. So do your best, and as always, if you need some extra help, then reach out. Until next time, take care.